Now we're going to go ahead and look at confidence intervals with an unknown population standard deviation. But before we do that, a little bit of Garfield. Taking a look at tomorrow's weather, the high temperature will be between 40 below zero and 200 above. And he says this guy is never wrong. Yeah, that's because he's pretty much used a 100% confidence interval, which we won't be doing because that's not very helpful. So, first of all, if I draw a sample from a population that has a normal distribution with a mean mu and standard deviation of sigma, then x bar will have the normal distribution where you have x bar and s for n sample size. Now, as n gets bigger, the spread or variance decreases because the better the sample size, the tighter our distribution. Now, most of the time we don't know the standard deviation of the population, but we can calculate S, which is known as the standard error of the sample. Now, problems were noticed when n was not large. So what does this go back to? Believe it or not, in a brewery. Some of you have probably heard of Guinness beer, good Irish beer if I recall. And he would use small samples to test the stout, which is a very heavy, filling drink. And he didn't want to drink a whole bunch. And I'm sure if the stout was ever bad, he really didn't want to drink it. And he wanted an alpha 0.05. In other words, he expected to reject 5% of the good batch. He's like, I can live with 5% of good beer being rejected. But he found out he was actually rejecting 15% of good batches, and that's too much. So he created a new model based on his analysis called the student's T distribution. Now, these students' T distributions are unimodal, symmetric, and bell-shaped. So right here, the red curve is the student's T curve when we have a lot of degrees of freedom, like 40 here. The standard normal curve, which we've been using, is a blue one. So what happens is our degrees of freedom go down. So as I adjust the degrees of freedom here, you can see that this is starting to come down a little, and then these tails are starting to get fatter. So they have fatter tails, which means we're going to have a larger margin of error compared to a normal distribution, and something I'm going to teach you about later called larger p-values. Now, t-values or t-scores are like z-scores or z-critical values, but have a different model for every degree of freedom. You can see this is degree of freedom 1, and when I had it all the way to 40, it looked a lot like a normal distribution. So as the degrees of freedom increases, this distribution looks like the normal. So this is how we'll use stapplet to calculate your t-value. You go to stapplet.com, click on t-distributions, and I'll show it to you. Under probability, so you have your first section of the data, and then you have probability. Look for t-distributions. Calculate a value. Remember, we're trying to calculate a critical value. So notice how it says a critical t-value. So that's your hint. We're not doing an area. We're doing a value. And then enter the degrees of freedom, which is basically your sample size -1. Select the center area because we want our critical value centered around our estimate. And so you're going to put the center area and the confidence level in decimal form and then click on Calculate Value. So use the student's t-distribution to find TC for a 0.8 confidence level when the sample size is 32. So what we first need to do is we need to know our degrees of freedom and our area. So our area is the center. Degrees of freedom is 32 minus 1, so it's 31. And let's go ahead and pull up the stapplet. So to find a critical value, you're going to have to use the t-distribution, which you can find on stapplet under the probability section. And since we're finding a value, we don't want the area, we want the value. The degrees of freedom has to do with your sample size. And you can see as the bigger our sample size goes, the closer to a normal distribution it gets. So what number should you use there? One smaller than your sample size. So our sample size was 32, but we're going to use 31. And then here you always click central because we're trying to set a confidence interval about the point estimate. For the area, you put in the confidence level as a decimal value. We had 80%, so we're doing 0.8. All right. And there is your value, 1.3095. So now we'll calculate it for a larger sample size. First, our degrees of freedom is 64 minus 1, so it's 63. Area is still 0.8, and it's still centered. Now we want to find a critical value for the same scenario, but a larger sample size. So that's just as simple as putting in your new degrees of freedom. Our sample size was 64, so we're going to use 63. Plot distribution. Area is always central, and we're still using an 80% confidence interval. And there is your critical value, 1.2951. So which is larger? The one with the smaller degrees of freedom, because we have more variability, less certainty with a smaller sample size. So now we have a sample of 50 randomly selected SAT math scores from Cedar Ridge, and they had an average of 570 and a standard error of 85. We're going to construct a 99% confidence interval using the manual method. So the first thing we're going to do is write down what we know. We have 570, 85, 50. That's N is 50 our sample size, 85 is standard error, 570 is the average, and our degrees of freedom is one lower than the sample size. To find the critical value in this example, we have a sample size of 50, so our degrees of freedom is 49. So we're still at the same t-distribution stapplet. I still have calculate a value because we're trying to find a critical value. Plot my distribution. In this case, my confidence interval is 99%, so I change that to 0.99 and hit calculate values, and I get 2.68. So we're going to go ahead and calculate our standard error for the sample. So this is standard deviation for the population, or standard error based on the sample, but now we have to create one for our confidence interval, which means we have to include the sample size. So we take 85 divided by the square root of n. You've learned how to do this in the last unit on sampling distributions. And there's a critical value that we just found. So our confidence interval is 570 plus or minus your critical value times your standard error for your sampling distribution. So we can basically go 570. If we multiply this out and subtract it from 570, I think we're going to get about 22. Yes. And then you subtract that, you get this, you add it, you get that, and there's your confidence interval. But there's an easier method. So first of all, we're going to go to the one quantitative variable single group, not the t-distribution, but the single group. We're going to select our mean. See how you can click mean and standard deviation on the input set up here. So it's very important to click that drop down. Enter the mean from your data. Enter the standard error for the sample. Enter the sample size, and then click begin analysis, which is right there. And then make sure you select a one sample t interval from you. Make sure you put in your confidence level, which is normally 95%, but not in this example. So we'll do a quick run through. Yeah, you can use the staplets directly to calculate your confidence interval without having to do critical t-values. So I'm going to hit one quantitative variable single group, and my variable name is SAT math scores. I can just say mean and standard deviation, put in the mean, 570, 85, and 50. Begin analysis. Do a one sample t interval. Normally our confidence intervals are 95%, but in this case we're doing 99%, so I'll go ahead and do that. And boom, there is your interval. So now that we have our interval, we can interpret it. We are 99% confident that the true average SAT math score at CRHS is between 537.78 and 602.22. So I kind of rounded slightly. Probably 538 to 602 would have been fine. But anyways, there you go. So in fact, you can see I rounded a little bit here. So based on the stapplet output, what is the point estimate and the margin of error? So what I'm doing is I'm kind of using a little number line to show the lower and the upper bounds on my interval. The point estimate is the midpoint. It goes right there. So it needs to be halfway. So I can for me, the easiest thing to do is just average these two. Add the 537.8 and the 602.2. divided by 2, and we get 570. All right. Then the margin of error is the distance from that midpoint to one of the edges. So either edge, the lower edge or the upper edge. I tend to do the lower edge because then I can just say point estimate minus the lower bound, and I get 32.2. And that should look familiar because when we did it by hand, we had our point estimate to start was 570. Remember, that's what we put in the stapplet. And we calculated a margin of error of 32.2. So now we have a coffee machine that's dispensing coffee into paper cups. You're supposed to get 10 ounces of coffee, but the amount varies slightly from cup to cup. Here are the amounts measured in a random sample of 20 cups. And they want us to do a 95% confidence interval. And now we're just going to use the stapplet. If you have raw data, that's the only thing I do anyways, so I would use technology. So here's how you do it. You still, this time instead of selecting mean and standard deviation on the right here, you're going to select raw data. You input your data, separated by commas or spaces. I tend to do spaces. Click on Begin Analysis as always, and then you're going to have to scroll down to the section marked Perform Inference that's below these summary stats, and select one sample t-interval. For your confidence level, enter your desired confidence level as a percent. Usually actually as a decimal. So it's typically 95%. So we'll do a quick walkthrough. We're looking for the mean of one set of data. So that's one quantitative variable because we have ounces of coffee. Just one group of data, the sets of coffee. So we'll say ounces of coffee as our variable name. We're going to stay with raw data. You can do mean, standard deviation, and you can do 5-number summary. Now I went ahead and copied the data so I could just paste it, and then hit begin, and then I come down to perform inference, and I select the one sample t-interval from you, and there's your confidence level. And we did want a 95% confidence, so I hit perform inference, and there's the output, lower bound and upper bound. So once you have the output, the lower bound shows the lowest plausible value for the true mean based on the interval. The upper bound shows the highest. So to interpret this, we basically say we're 95% confident that the true value, pretend that says value, of coffee, volume of coffee in ounces, dispensed in each cup is between 9.752 and 9.938 ounces. And that's